This is an update on the work-in-progress redesign of the phone line simulator using the KS0835F SLIC module subscriber line interface circuit, where almost a year ago I did the first PCB prototype of this with an ESP-8266, but it wasn't powerful enough, didn't have enough GPIO, and I'm starting over using the ESP-32 on a DevKit V1 Do-It module that has 30 pins. There's several available with different amounts of pins and different GPIO broken out to be available. So I settled on the 30 pin because I have several of them, and I think I have just enough pins available for what I need. As a review of what it takes to get a landline phone to actually function and be able to connect to another phone, it's probably easiest to look at this circuit block here, which is basically where some phone jacks are located, and we can connect this entire station to some other duplicate station via phone cables, so we can have one phone talk to another. So this is going to be our local phone, and what we need is a way that when we pick up the phone, it's not just like a dead phone line. You can actually hear a dial tone and press buttons on the phone or rotate the dial if it's mechanical, and you can get interactions and you can hear the activity going on. Or if the phone is on hook, you need something to be able to generate ringing signals so the phone can ring. So this tip and ring here goes to another schematic page which controls this local phone, making it ring or giving it power to operate. And the idea is we have two duplicate setups like this entire schematic with two separate phones that you want one to call the other, and when it's time you need them to connect up so the audio can pass back and forth. So that's what this part of the circuit here does. The local phone is plugged in here and is controlled by the SLIC module. When it's time to actually let one phone talk to the other phone, all we need to do is connect the tips and the rings of two different phones together in a way that only the audio can pass between the two stations and the two phones. Otherwise, any ring voltages you just want to stay local to the phone being controlled, and any actual loop current that makes the phone alive just stays local, and we just want audio to pass. So if we have this set up where one phone on one circuit board is going to call the phone on another circuit board, and they coordinate to complete this call, the ESP-32 can turn on this transistor, which closes the contacts on this relay. Then the tip and ring of the local phone gets connected to this capacitor and transformer, which DC blocks and isolates this one phone physically from the other, but audio can pass through both directions. So the ESP only makes this connection between two phones when it's time to send or receive audio, and the SLIC module takes care of just operating the phone electrically. So back at the high-level schematic, the control signal comes out here to connect the phone on this board to a remote phone. Otherwise, the tip and ring of the local phone as well as the remotely connected phone get connected over here to this SLIC module circuit block. And this SLIC module has 3 control pins. So this allows the ESP to tell the SLIC to generate a ring voltage so the local connected phone can ring when it's time. Otherwise, if somebody picks up the phone off hook, this SLIC module can tell the ESP the phone was just picked up, and so it's time to do stuff. The SLIC module also has an audio in and out path. So in addition to talking into one phone and then having audio come in over the phone line from another phone that you can hear, you can also tap into the audio and listen to these phone signals on another circuit, or you can send audio into this module and that audio will go over the phone line as if somebody were talking. So that part of the circuit is useful because if somebody picks up the phone and starts dialing, we can take that audio and put it into this DTMF decoder, and then this will tell the ESP what keys somebody is pressing. So it knows you're dialing a number. And also if we want to use the ADC on the ESP for some purpose to do something else with the audio, we have that capability here. Generating audio out of the ESP to go into the phone line is useful because that's how we can generate things like a dial tone when somebody picks up the phone. That tells them the phone is active. And the other call progress tones, like if they just dialed a number and the other end is busy or ringing, those tones are played from the ESP into the phone line this way. So if we go look at this SLIC schematic page, this part of the circuit here is the actual SLIC module and the recommended support components, which were looked at previously, where I made a separate dev board just with these parts to do initial experiments. The tip and ring of the phone line come out here and go to the other circuit blocks to connect to the actual phones. Control signals from the ESP-32 come in here, and when a phone is picked up off hook, the SLIC module sends an output signal to the ESP-32. But this signal has a lot of bounce on it. I think it's something like 10 to 15 milliseconds that this just quickly goes high and low when picking it up or hanging up again. So I just did a little bit of filtering here to smooth out that signal. And I had an extra buffer, so I thought I'll just use it here and clean this signal up a little more and send it to the ESP. And this switch hook signal can obviously be debounced in software on the ESP, but it generates so many pulses. I'd rather just send a more clean signal in and not be triggering an IRQ so much and things like that. And here we have a bandpass filter on both the audio going into the phone and coming out of the phone. This is approximately 300 Hz to 3.4 kilohertz, which is the regular landline audio range of frequencies. And this filter circuit and this whole structure right here on the audio coming out of the SLIC, going into the rest of the circuit board, that's been reviewed. So there's a Zener diode clipping circuit here because an anomaly was observed where even though this is an audio path, which should only have regular audio signals, when the phone is ringing, there's this extra 7.5 volts peak-to-peak weird signal that shows up on the audio path. So this circuit here evolved to help restrict that from causing too much of a disturbance, keeping it within the regular audio range, and filtering the audio to the normal phone pass band, biasing it up to make sure it stays between 0 and 3.3 volts so it can go into the ESP's ADC, staying within allowable positive voltage range. And this FET transistor here allows muting the audio coming out of here in case we want to be able to not have any sound passing through at the time when this ringing disturbance is occurring. Because even though we're clipping it and trying to do some signal conditioning on it, it still could just sound aggressive and not the kind of audio we want to hear. So we have an option to mute it altogether here. Those kind of features are what kept evolving while working on this ESP-32 version of this phone line simulator. So that covers getting a phone line up and running, having a phone ring, being able to get audio in and out of the phone, and connect one phone to another phone on a duplicate setup like this, connected by a phone cable. So the DTMF decoder listening in on the audio path is waiting for DTMF key presses to be heard. And this is the standard circuit for the MT8870 DTMF decoder. It takes that audio out of the SLIC module, and when it hears a valid touch tone key being pressed, it signals the ESP that a key's been pressed, and then there's 4 bits here to decode which key has been pressed. The reason we have buffers here, the 4050 acts as a level translator because the ESP is 3.3 volts and the 4050 is powered from 3.3 volts, but it has 5 volt tolerant inputs. And this DTMF decoder chip can only run on 5 volts, so these outputs need to be scaled down to 3.3. And this could simply be done with a voltage divider resistor on each of these signals, but the physical space for 10 resistors compared to one of these chips, you might as well put a chip on the board, plus you can clean up the signals and not even need to worry about voltage tolerances with the two resistors and exactly what voltage is being driven. It just regenerates a clean 3.3 volt compatible signal. Then the power supply block is where we put decoupling capacitors on any of the chips, and it's set up so that anything that runs on 3.3 volts has an onboard regulator that takes 5 volts to give a 3.3 volt rail. The op amps are running at plus and minus 5 volts because it gives more signal headroom to work with compared to just a 5 volt and ground powered op amp where you have to shift the signal up and you have less room to do things. So I've already got a plus 5 volt supply, and I'm using the ICL 7660 negative voltage generator to take 5 volts and convert it into as close as it can to negative 5 volts for the op amp. The more current that's drawn out of this, the less negative voltage you're going to get. So the idea is we may not get exactly plus 5 and minus 5. It might be plus 5 and minus 3 even, but that's still giving enough headroom to work with for this system. And as for the 5 volts main power, the SLIC module itself can draw a couple of hundred milliamps, plus the ESP-32 using Wi-Fi can use a couple of hundred milliamps. So I didn't want to just power this strictly over USB 5 volts, but for prototyping it still may be okay to run it off of USB only, just to do some testing without expecting everything to run smoothly. And I could have put some sort of auto power source switching circuit here, sort of like the Arduino Uno automatically switches between external DC power and USB power. But for these purposes, I intend long-term to use external power to get enough current for the whole board. So the jumper would ultimately just be across pins 2 and 3 for external power. But in the meantime, if we only have USB plugged in, the 5 volt USB power comes here. And on the ESP module, it's got a series diode, so it's slightly less than 5 volts. So that will come to this jumper pin 1, and we can put the jumper across pins 1 and 2 so that USB power is what gets to the 5 volt rail and then powers the rest of the board. While the jumper is in USB power mode, if we do have external power plugged in, we'll be generating another 5 volt supply with this regulator, and it's also got a series diode that connects up to the USB 5 volts. So these two 5 volt sources can be present at the same time, and whichever one is there, or if both are there, that will power the 5 volt rail if the jumper is across 1 and 2. But there's a reason I wanted the opportunity to just give straight 5 volts out of this regulator without any diode drop as a power option. This regulator has a tight tolerance. I think the minimum guaranteed output voltage is 4.9 or close to it, where some other 5 volt regulators may go down to 4.7 or so. But I wanted to make sure I can get at least 4.75 volts on the 5 volt rail, because this DTMF decoder chip has a datasheet recommended voltage range that goes down to 4.75 volts. So if we're powering this chip from the ESP-32 5 volt supply, and it's got a series diode drop, it's already possibly down to 4.7, which is violating the minimum power needed by this chip. It's probably fine, but I just wanted to make sure the specs are achieved. So that's why this jumper here, giving maybe a minimum of 4.9 volts, will guarantee everything on the board can run properly. Plus, by having an external DC source, and this regulator can do well over an amp, USB is not going to give us as much power, and we may have losses over the cable and such. So it's better to just have a more stable power supply to run this system, since it does use possibly half an amp between the ESP module and the SLIC module. So that's how these separate circuit blocks are configured and how they all work for this phone system. Otherwise, for a status LED, I wanted to be able to just simplify it down to one LED instead of 5 or 6 that show different status results, like off hook or ringing or making a call. In order to have an RGB LED that can do different colors or even blink patterns, I put these two options here, a discrete RGB LED here that we can PWM, or if this is not installed, I put a 5-volt ground and data signal here to plug in an addressable LED like a WS2812, so we can use that instead depending which one's preferred. I want it to be able to test with both. And in case it makes more sense to play back some audio off of an SD card instead of trying to fit it all into program flash, I wired up the SPI pins to this header here so I can plug in a generic micro SD card module, and we can put a lot more things like MP3 messages like hang up and try your call again, this is a recording, or whatever else, and we can play those into the phone line. For generating stuff like call progress DTMF tones, pins 25 and 26 on the ESP module can be used as an internal DAC to generate audio, but I also wanted the option of an external DAC, so I have the 3 I2S clock and data pins here going to a header where I can plug in this external I2S DAC, and if I do that, I want to cut this jumper so the ESP is not sending audio out, it's just using this as a data pin into the DAC, then the DAC sends audio out into the phone system. So this signal here gets cut. We only use either the internal DAC or this external DAC. I just wanted to be able to try both options. Because depending on what software libraries are used and what features they have, that may make it better to use either the internal or external audio options. So this is really still a prototyping platform, work in progress, and I'm ready to make another PCB at this point as is. So I'm going to go ahead and order boards, and when they come in, I'll start working more on the software and see if I can get a complete system working. And maybe I can optimize away some things, like choose one or the other type of LED, or whether I need access to an SD card, or if I want to use an external audio DAC. So that's where this project is currently sitting, and it's going to be worked on in the next few months. There's also this jumper here, which is related to ESP Wi-Fi. Basically, whether it's installed or removed, it tells this ESP module on one board or another board whether that board is acting more as a master server board or a slave sender board, which sends its data to the master when requested. That's just a part of how these modules are going to auto-join. One of them has to act dominant and the other one not so much. And long term, I may not need this jumper. I could either just set a switch when I'm compiling, and that would be dedicated software as a master or slave, depending which board I put it in. Or if I have an SD card, or I can use program flash, I could store the status in there. But for prototyping, I just put a jumper. So some of these features may change in the future. I may also decide if I'm getting close to a final solution, I may opt for downsizing this with surface mount stuff. I have some surface mount DTMF decoders and surface mount level shifting buffers. Obviously, passive components are smaller when they are surface mount. I can use surface mount op amps. Some of these things like these diodes may stay through hole to be more robust and readily available. And other things like the relay and the phone jacks, the DC block capacitor and the transformer for the phone line would stay through hole, and probably the voltage regulators as well. But I'm already maxing out the 100 by 100 millimeter board size for the flat rate overseas PCB ordering, and beyond that, the cost goes up. So if I can finalize a design, I may leave it through hole, but I may go surface mount. So there's still a lot of work to be done, including especially software, but maybe more hardware optimizing as well. So that's where this project is at. It's almost been a year since the ESP-8266 version was tested out and its limitations discovered. So now we're getting back into full testing with the ESP-32.